Good morning, everyone. I think we are going to start with the scheduling. Is it so? Just drop me a message, confirm, so we can proceed. Uh, should we start with scheduling? I think so. Anyone can just confirm, yes or no?
Yes, sir.
Yes, all right. Thank you. So I'll get started scheduling, which in itself is very interesting because for multi-programming computers, we understand that the OS is a controller of uh, processes. That's when it comes to process management, that's what OS is doing. So basically, where we stand, why we have to study this schedulers. So we understand there are two ways that there are basically two things that um, kernel keeps an eye on and kernel uses to keep things switching. Let me pick up a pen. The first one is process table. We understand. And inside the process table, for each process, we have a number of PCB. Very important. Kernel keeps an eye on that. That, as I said, it is the real-time health checkup or performance sheet. Okay. So basically, whatever the process is doing, every minute details are noted down in the PCB. And number two is the scheduler. What we have in the scheduler, an algorithm. An algorithm. An algorithm. And why do we need the algorithm? Because based on these algorithms, the processes will get switched, or the CPU will get switched. All right. So that is how your kernel OS continues to control the processes. The review part, these slides, I like the review part because that gives you a quick reminder of the things that we have already studied in this chapter. In last class, we talked about IPC. They just highlight the points. Now here we are. But before we jump into those algorithms, we need to understand, talk a little bit about the process behavior, when to schedule, and categories, criteria. And finally, right here, we will get started today with uh, three algorithms, for the batch processing system. Okay. And as we understand, the algorithms will be different for different platforms, so different kind of systems. Then in the next part, we'll talk about interactive systems and real-time systems, and a little bit about thread, because thread is primarily not implemented in kernel, because their implementation is in the hand of the RE, or the runtime environment, which is a third-party software, so we don't deal with that, and we're not aware of what is in them. So after that one, we will move on to talk about some classic IPC problem, just hint at it, and that will wrap it up. And that will be the end of chapter 2. So I think that we will be needing Friday as well to finish it up, finish this chapter. Anyway, let's focus on process behavior. First, the introduction. Another thing, in these particular slides, you'll be learning lots of new words. These are technical words, and we do use these words quite often in computer science, not only here, but elsewhere as well. So learn these words very well. Okay. This will be extremely helpful for you. Scheduler is an OS component, and all it has is a scheduling algorithm. Clear? And we already understand that part. They support the kernel level threads, as we said, it is the threads that are being scheduled, but we understand very few OS actually support kernel level threads because that will be a huge compromise in speed. And threads for multi-threading stands for speed, okay, higher levels of speed. So we usually don't do that, and we give the control to the hand of RE or runtime environment, like your JRE, Java Runtime Environment. And runtime environment is just another third-party software running in the user space. So naturally, we are not worried about we are not bothered about what sort of algorithm is written inside the RE component. Yeah. If you look at a little bit of history, nothing much in it, but only one thing that we can pick up from this part is that things are changing. In older times, it used to be a very simple algorithm, but now the things have become more logically complex. Okay, because more tasks and more functionalities have been added, and the user expectations, all these things have happened because user expectations from the machine has been changing rapidly. All right. So naturally, to keep pace with that, we have to change those algorithms and make them become more sophisticated. So that is the more sophisticated at the bottom. So that is exactly what we're going to study. So first we'll just learn a handful of algorithms. The easiest one, and then probably two other versions where the things will get a little more complex. It's all about logic. Process behavior is an important thing, and there we already know the concept that we are going to talk about. But here we are going to re-emphasize on that little part. In fact, we call it process behavior, but you can also think about it in terms of CPU task, while executing a process. Okay, you may actually think about this in terms of that as well. So it's a CPU task while executing processes. That what's that CPU do? Well, whatever you call it, we need to understand that there are two ways to do that. That all the processes, irrespective of whichever system we are referring to, they run when they execute CPU. They run in two bursts. This is what we call the burst mode. Sorry, BURST, burst mode. CPU burst, IO burst, as you can see right here. Execution consists of a cycle of bursts of computing that is called CPU execution and IO request. CPU execution, IO request. So sometimes the CPU is busy, literally what it means from the CPU's point of view. Sometimes CPU is busy doing computation. Sometimes it's waiting for IO. Sometimes it's doing computation. Sometimes it's waiting for IO. So basically, if it is doing computation for too long, in the meantime, when it was busy in the computation, and you keep hammering on your keyboard or try to give an input, that input will not be registered or accepted. Okay, because computer needs to be, or your process needs to be in the IO mode to receive those inputs. Yeah. Now, based on that, this is the pattern of execution. Based on that, we have two different categories, broadly speaking, two different categories of processes. The first one is compute-bound processes. Some of the processes are called compute-bound processes, where, as you will see, obviously, we spend, or these processes spend much of their time on computation. So long computation bursts and infrequent and short IO bursts. Then again, a long computation burst, and then short and infrequent IO bursts. So if that is the feature, then we can easily say that these processes are compute-bound processes. This is a process categorization based on their behavior. An example for that is most of the batch system processes or batch processes are compute-bound processes. Okay. The second one, IO-bound process, just the opposite. The frequent and IO burst followed by short CPU burst. Short CPU burst, frequent IO burst. If that is the case, most of their time waiting for IO, have short CPU burst, those frequent IO waits. An example for that is real-time process. So where is our PC? Personal computer, interactive computer. Interactive computer, as you may guess, is almost equal. Short, then short, then short, 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 short. So in this case, it is short CPU burst followed by short and frequent IO burst. So frequent CPU burst, frequent IO burst, short CPU, short IO. And that's how it becomes so the machine, our machine becomes so responsive. Now it becomes responsive because responsive means that you press a key and you press the key in your own sweet will, and there's no prediction, no algorithm that when exactly you're going to press the key or click a mouse. But whenever you do it, your machine is always ready to accept. Right? So that's the pattern of process behavior for most of the processes. That's what they're doing while CPU is executing on them in our interactive systems. So we have this knowledge of process behavior that will help us to understand the switching actions as it takes place. Next big question is sorry. Next big question is when to schedule. When to schedule. Normal that when we ask this question, the first thing that comes to our mind is when switching or context switching takes place. Right? Context switching, that means a process keeps changing its states from running state to block state, running to ready state, ready to running state. That is when we need to schedule. But apart from that, on top of that, actually, we do have certain other situations where we may need to schedule. For example, process creation. When a process is created, a decision needs to be taken whether to send it in normal conditions, send it to running, or ready. If your OS supports hierarchy, process hierarchy, like parent-child hierarchy, like in Unix, then you also have to take a decision on which one to run first, the parent-child or the child, a parent or the child process. Termination, when a process gets terminated. Okay. Now, termination can be of two types. One is voluntary. Another one is involuntary. We already learned about that in the process part, right? Voluntary is usually done to a system call. That's normal exit. An abnormal exit, it's basically when there's a deadlock and it happens to a hardware interrupt. Because the hardware doesn't know what to do and it keeps an interrupt, sends in a kind of an SOS, you might say, SOS to the kernel to do something, and eventually kernel understands and kernel will try to snatch the resource back or do whatever it can do. If it can do something, it will do. When it receives an SOS from from the hardware. So in both these cases, we need switch. Blocking. Again, another process has to be selected to run. This is also another part where we need switching. Then the next important one is interrupt. We already saw that interrupt occurrence. An interrupt can happen for many reasons. The most common interrupts in your computer, and these are normal interrupts, happen when we have an I/O. Okay? Because I/O comes from hardware devices, and whenever a hardware device wants to talk to the system or to the kernel, okay, usually by sending those SOS messages that something suddenly has happened on me, please take action. That's the kind of message to send, and they do it through what we call interrupt. Like you click a mouse, you press key of the keyboard. These are all interrupts. They're all general interrupts. We know it categorically, but we'll study it in more detail in the next chapter. Not next chapter, the chapter later. So we have the interrupts. But there's also another kind of interrupt that is called clock interrupt. In fact, while we are here, I would like to mention two things that I prefer to clock. I prefer to refer to these hardware. Clock is a hardware. I prefer to refer to this hardware as the heart of the computer. Now, we often say that CPU is the brain of the computer. So naturally, what is the heart? Well, these are all analogical. It needs some logical interpretation. In my opinion, it's the clock. And we'll see it soon why we call it. In fact, we'll study the clock separately later. Now, it is a heart because it is a hardware. It is essentially a pendulum, an oscillator that, just like a swing, you take it to a certain displacement and let it go, and it will swing, 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 until it comes to standstill. When it comes back to the standstill, again, to its original position, displacement 0, then it generates an interrupt. So what is special about these clock interrupts is that these are predictable interrupts at periodic intervals. Predictable interrupt, because as we said, the word we choose to use the word interrupt is simply because all these interrupts are unpredictable. You just don't know when's the next time the user is going to press. Unpredictable. So these, while interrupts in general are unpredictable, the clock interrupt is periodic and predictable. So we use these interrupts, we gather up these interrupts. An interrupt is an interrupt. This clock interrupt, as I explained, is not 1 minute or 1 second or 1 millisecond or 1 nanosecond. Then there's a software, clock software, that works as the driver, the controller of the clock, in fact, the driver of the clock, that gathers up all these interrupts together and will reinterpret it in terms of real time. And that's only possible because these interrupts are predictable and happens in periodic, periodic intervals. That means at regular intervals. So we know exactly how to calculate how to interpret bunch of interrupts, clock interrupts to real time. And that's what it does. The reason I called it hard is because later we will see in most of these algorithms, and not only here, but also many of the CPU and kernel actions are firmly based on the perception of time. So if you take the clock out, or if the clock stops, your computer will not have any perception of time. That means all the algorithms, I should say, all the algorithms in your personal computer will fail to execute because there's a time factor embedded inside those algorithms, especially for the interactive systems. So if these algorithms fail, then the switching action will fail as well. So your computer will come to a standstill or literally freeze. Not only this, that CPU uses the clock, okay, to constantly update the registers. So that too will fail. So everything will be dead. So remember, if someone asks you in a casual way that if CPU is the brain of the computer, what do you reckon is the heart of the computer? Well, you can easily say that it is the clock. And you have ample justification now to justify why you claim so. Then finally, the CPU switching, running to block, running to ready, block to ready, and terminus. So these are the things where and when we need to schedule. Clear? I've tried my best to highlight those things. Now, we already found these two words right here, very, very important words, non-preemptive and preemptive. So let's talk about these two new words, and you'll be finding these keywords, these words elsewhere in computer science, and to some extent again in the last chapter. Preemption and non-preemption, preemptive and non-preemptive. So preemptive literally means that you are making a guess of something, or you are rather anticipating what is going to happen next. For example, sometimes in plain English, in general English, we say we took some preemptive measures to prevent a fire in this house. So that means we already try to imagine the situation that we have fire breaking out in this house, and we try to find out what could be the root causes for that. And we tried to take some actions based on our assumption to try to somehow disable those possible reasons of a fire. Did you get my point? So I made an estimation, made an assumption that these could be the reasons because of which in future a fire may break out in this house. And we already tried to negate those factors to prevent a fire. So this is what we call preemptive actions. In the context of clock algorithm or switching, CPU switching, preemptive algorithms are the algorithms that allows a maximum time to maximum limit of time to each of these processes or CPU. So they make an assumption that a process might take just this much time to keep running. Okay. So that is an assumption that they make. And this assumption is very important. So this assumption will help them to keep going with the switching. So if a process gets CPU and starts running, it knows exactly for how long it is going to run. And then it needs to get switched. And that is exactly what happens when these processes gets switched with preemptive algorithm. So now we understand what is preemptive. And how about the non-preemptive? The non-preemptive, just the opposite. We don't make any guess about the speed of the processes or the time that will be allowed for the process execution. So basically, if a process is currently running on CPU, then we just let it run. We don't want to interrupt it, and it keeps running as long as it wants to run. But in the case of preemptive algorithms, no. It can run only for a maximum time limit that has been promised, right? And after that, it must get switched. So that is what we call the preemptive and non-preemptive algorithm. As I've highlighted, easy to understand, the preemptive, non-preemptive algorithms are good for batch systems because we already know what batch systems do. Spend most of the time on the computation, right? Most of the processes are compute-bound process, number one. Number two, they spend most of their time on CPU. So naturally, there won't be any interruption. And preemptive algorithms are primarily used for time sharing, that is our personal computer, interactive machines, and real-time systems, where multiple processes need to get set. So that is what we do. Time sharing machine. Moving on. Categories of scheduling algorithms. So how many different categories of algorithms do we have? Now that is something very interesting because broadly speaking, the algorithms that we'll be looking at have been grouped together in three different categories. One is a batch system, was interactive algorithms, and the next one real time. So basically, those algorithms mostly applicable for interactive systems. Those are mostly applicable on batch processing systems, and those algorithms which are mostly applicable for the real-time systems. So these are the three broad categories we usually look at. And in terms of preemptive and non-preemptive, as you can see, the batch systems must be non-preemptive, but in general are non-preemptive. But we can use preemptive algorithm, but in that case, we must give them ample time to execute fully on the CPU. So we must give them a long time interval, right? And for interactive, with long periods of each process. For interactive, definitely preemptive. Real time, definitely preemptive. The difference of interactive and between interactive and real time categories is that, well, when it comes to the algorithms, of course, they're preemptive. But usually, for the real time, there must be a strict deadline for the time of execution. Okay, and that time is very critical. So, although we use preemptive algorithms inside the scheduler, but sometimes, and most of the times, it's not needed because the processes, the real time processes, they have their internal time limit. They know exactly how long they're going to run. So, no need for the scheduler to intervene. So, basically, that is what we have right here, the real time and interactive and batch systems. Policy, the thing that we are going to study in this part is all about criteria. What are the criteria that we have? Now, when we talk about the criteria, the, the first question that comes to our mind is the first question that comes to our mind is what are these criteria for? What are these criteria for? Now, these criteria we'll be using to evaluate efficiency, the efficiency of those algorithms. Of those algorithms. Yeah. So we have this criteria that we'll be using to evaluate the performance and the efficiency of the algorithms that we write, the scheduling algorithms. And of course, in different contexts, because as we understand, they they are not all in the same category. Okay, we have three different categories. Just now we mentioned it. The first couple of them, in fact, there are three of them. This category, these criteria, these are the criteria that will be applicable to all kind of algorithms, irrespective of whichever category they fall into. So whether batch, interactive, or real time, doesn't matter. All these algorithms can be judged based on these common criteria: fairness and policy enforcement. Now, there's a couple of words there. As you can see in the fairness, we use the word equivalent. Now, equivalent processes will have equivalent secure time. Now, equivalent is a word, and that doesn't exactly mean of equal size or anything like that. The equivalence of a process can only be estimated or judged or compared by the kernel. Okay, only the kernel is aware of that, and the kernel can do its calculation to understand which two processes could be considered equivalent. And kernel does so by keeping an eye on all the registers that have been recorded on PCB. So that is what is happening. That is what we call the fairness. Policy enforcement is another thing, and it is a very important thing. It depends on several factors, the kind of policies that you will have to adhere to while writing an algorithm. Right. Now, that can be related to a lot of things. It could be some business policies of the organization. Then it could be related to privacy policy of the user, the data related policies. These are the policies that we encounter the most common. It could even come from the government policies. Yes. And wherever the policy comes from, these policy enforcement, these policies must be implemented. And while we try to implement it, we need to find a mechanism. Okay. Now, so that's what you call the fairness and policy enforcement. These two factors will always be there before you start judging. We use the other criteria to judge the performance of your algorithms. Now, some new words. Throughput, for example. What is throughput? These are new words, and you will have to remember these words. The number of processes that complete their execution per unit time. Throughput is one of the most common criteria we use to judge the batch category algorithms. Okay. Turnaround time, amount of time to execute a particular process, that too applies to batch. In fact, it may seem that it is a good algorithm for interactive processes. Well, for interactive processes that run on their own, where process switching is involved, okay, turnaround time is the best way to do it. So basically, amount of time to execute a particular process. So what you need to remember is if a process starts here and then it executes, then it is off, 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 executes again, off, 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 executes again, and here it terminates. This is the termination point. If you think that this is point 0 and this is point x, so the turnaround time will be x minus 0. That means it's good to remember how we calculate. This is the processes, this is what we call the process burst time. So there are two words. One is burst time. Right. And these parts are called waiting time. So turnaround time literally means turn around time is bus time plus waiting time. Because later we have to do these calculations. So please remember this factor. The bus turnaround time plus the turnaround time literally means the bus time, the process bus time, and the waiting time. Amount of time to execute a particular process. Yeah. Then comes CPU utilization, also a factor for a criteria for batch systems. Okay. Where we already know what is CPU utilization, how could we increase it? By increasing RAM. And what is the logic behind it? That if you have more RAM, you can load more processors. So now you can share your CPU among more processors, and that's what we need to increase CPU utilization. Heavily used system, 90%. That is our target. This is for batch systems. Then response time and proportionality, these two are for interactive systems. Or I just simply write PC or personal computer. Okay, interactive system. What is response time? Response time is that when you assign a task to a running process, how fast a reply is generated. The task is performed. It's more like we know response time. You open a browser. Okay, a browser is an app which is running. It's not about for how long the browser takes to run to completion. That will be turnaround time. But that is an impractical thing because that really depends on the user these days. So we don't consider turnaround time as one of the criteria for these interactive processes. So what we do, interactive algorithms, in fact. So what we do is we focus on response time. Then how fast, if I want to search in Google, if I want to search for something, or if I just move to one page to another page, of course, there are many other factors there, including the bandwidth and the speed of the internet and something. But how fast we can move from this part to that part. Okay. So that is what we call the response time. And the proportionality. Proportionality is simple. You think about the two applications that you have, all of us, we have, and you may have, because not sure if you're studying Java. Say, Notepad is the one that we all have. And on the other hand, say, NetBeans. Not sure if you have heard about that. NetBeans is an IDE for Java. Okay. Now that's a robust platform. So when you want to start Notepad, it just gets started in a split second. The window pops up. But when you want to run NetBeans, you may have to wait for 4 minutes, 5 minutes, depending on the hardware speed. 4 minutes and 5 minutes. So what we have, the proportionality, as we say, the Notepad and NetBeans. We do expect that NetBean will take a huge amount of time. That we understand. Notepad, on the other hand, is a lightweight software that will just jump up from nowhere. Okay. But if you see on your system, because of those OSL algorithms, a Notepad is taking as much time as it takes for the net wins. So definitely you understand there must be something wrong in it. There must be something wrong in the algorithm itself. So that is what we call proportionality. That's what we call proportionality. So proportionality and response time, these are two important criteria that we often use to judge the performance of interactive algorithms. Right. This is kind of a summarized version, and it could be very handy just in case you want to remember all of them. And these are the questions that we ask, that where exactly we use this kind of algorithms. So we have so as you take a look at it, for all systems, the criteria are fairness, policy enforcement, and balance. For the batch systems, it is throughput and turnaround time and CPU utilization. For interactive systems, is response time and proportionality. Okay. For real-time systems, it's about meeting deadlines and predictability. Clear? So these are some of the things that you will have to remember, because we do ask questions like which one is the criteria for what kind of algorithms. So that brings us to the beginning of that algorithm part in general. So in this slide, I mean, the slide that I'm using in this PowerPoint file, so we will first talk about the batch systems. There are three algorithms, three batch algorithms. The batch algorithm, and then from the batch algorithm, we will move to interactive algorithms. We'll see a handful of them, and then we talk a little bit about the real-time algorithm, and then thread and IPC related problems. First come, first serve. Now, since this is the first time you're going to get started, with algorithms, I must alert you that for any algorithm that you'll be studying out after this one in different other chapters, next chapter, and then chapters after that, everywhere we will end up with a handful of algorithms. Whenever you study an algorithm, a few things you must remember or pay attention. The first is you have to remember the full name and the abbreviation. The abbreviations, don't ignore the abbreviations, because most of the time in the question paper, I've seen the question setters, they don't go for the big name, they just go for the short abbreviations. Okay. And number three, equally important, is the context of this algorithm, because as you understand that you have 5 different chapters, and in 5 different chapters you will have 5 different packets full of algorithm. Okay. And some of these algorithms are absolutely the same algorithm. For example, right here, we are talking about first come, first served in memory management somewhere. We will talk about FIFO, first in, first out. And you understand that logically they are the same. But of course, they are being implemented in a different context. So their behavior will be slightly different, but underlying logic is still the same, that first in, first out, or first come, first served. Okay, so context is important. Now, from the algorithm's point of view, we rarely, I can't even remember uh, ever seeing that sort of question, that we hardly ask you to give a definition of an algorithm. It's not the definition, it's the logic. You have to understand the logic inside all these algorithms because most likely we will give you a case and you have to solve the problems, you have to tick the correct answer, you have to do some calculations on a piece of paper. Okay? And you know to answer those questions, you have just 1 minute. 60 questions, 60 minutes in operating systems exam, in the final exam. So you really should understand the logic behind those algorithms. Okay? So this is my general advice. Now let's move on to first come, first served. It is a non-preemptive one. It says that whichever process comes to the CPU first, gets to the CPU first, it will continue to run. It will continue to run as long as it wants to take. There shouldn't be any interruption of any sort, and the OS has literally no power to jump in and snatch the CPU back from the process. The process will continue to run until it blocks itself or terminates voluntarily. No interruption from OS. So it's just like we go to the ATM and we stand in a queue. The first guy who came first will be the first person to go to ATM, and the second guy will follow. But there is a problem because being non-preemptive, the second guy has no choice and no option whatsoever to disturb the first guy when he's busy on ATM. But unfortunately, the second guy doesn't know how long he will have to wait in the queue because that's our experience, right? So sometimes we're lucky we get a chance to go to the machine as quickly as possible within 3 minutes or 5 minutes. But sometimes for 30 minutes, for 1 hour, we have to wait. That thing's going to happen as well. So that is one of the drawbacks of a single queue non-preemptive algorithm, right? We'll see a quick, how do we judge its performance? So here we go. Don't have to understand the logic. Now, as you look at it, I will add another phrase. And this is the most common phrase that you will, common expression that you will see in all the questions related to scheduling. They start the question in the question paper by saying, and I quote, assume that P1, P2, and P3
teacher.
Oh,
I think your mic is not working.
yes. Sometimes it touch it and I can't remember. So what I'm talking about, that if you look at this one, this optimal algorithm that we have, we understand that first of all it is optimal. But if you look at the calculations, just be careful, because when they are calculating the average turnaround time, then there could be a little bit of confusion, because 24 is the turnaround time for P2. So they shouldn't have placed it at the end. I know why they have placed it at the end, because P2 finishes last. That they should have followed a certain order. Okay. So P2 has 24. Basically, the waiting time is 16 and the boss time is 8. So 8 plus 16, and that is 24. So pay attention to that and don't feel confused. Now we are moving on to the last one in this part for batch processing systems. And this is going to be the most important one, and frequently asked frequently asked algorithm in the exam. This is one of those algorithms that most of the time uh, your examiners, your question setters, they will have a question from. So be careful about this particular algorithm. It's called shortest remaining time next, or SRT. Shortest remaining time next, in fact, is a preemptive version. In fact, it works like a preemptive algorithm. In fact, probably in your book, they will refer to it as a preemptive one. In fact, it is preemptive because this is the one where the things are getting switched. All right. But I would rather say that it is not a pure preemptive algorithm, because in preemptive algorithms, as we already know, there must be a time limit, okay, a quantum of time, a time factor that must be embedded into the algorithm itself. But we don't do that right here with this particular algorithm. We don't do it. But still, through overall performance, it actually behaves like a preemptive algorithm because it keeps switching. But it somehow logically gets a perception of time, and that is what we are looking at. And it does so by taking into account at every moment, whenever a new process arrives, it takes into consideration what is left. Okay. And by taking care of what is left, it knows exactly which process should be allowed to switch to CPU or work on CPU next. So the important thing is, you can access to that. Take your time to understand these calculations, the calculation that they have done. If you have question, if you don't understand, please let me know. This is very, very, very important. A very important algorithm. Okay? And just let me know if you don't understand any part of it. Take your time. How did they do the calculation? So as we can see, the first thing, pay attention to the picture below, and that is what you will have to do if they ask you this sort of questions. P1 came first, arrival time 0. So P1 took the CPU. But P1 needed 9 bursts to finish its task. But after 2 bursts, P2 arrived, because P2 arrived at burst 2. So compare how much is left for P1, 7. And how much is left for P2, the new process, just 4 bursts. Which one is the shorter? P2. So P1 is off, P2 takes over, right? P2, after 1 more burst, after 2 more bursts, at a burst number 4, as you can see, P3 arrived with just 1 burst. So when we are in the burst number 4 right here, when with the burst number 4, we quickly look at it and we understand that it is the P3 that is the shortest, because P3 has 1 to go, P1, P2 has still 2 to go, and P1 still has 7 to go. So the shortest one is P3, the new process, and we switch the CPU to the new process P3. So P3 will be running. And how about the other one, P3? When P3 finishes its run, then what happens? When P3 is done, at that point, P4 arrived, because P4 arrived at burst 5, and it was asking for 4. So which one is the shortest? P2 still has 2 to go, P1 still has 7 to go, P4 still had 4 to go. Definitely P2. So P2 comes back, as you can see. And then after P2, only P4 and P1 are left, because no other process came there, and they got switched. Naturally, P4 fast, and P1 came back at the end to finish its 7 remaining bursts. And now you do the calculation of waiting time and turnaround time. Okay. So that is what we do and how we calculate. In fact, if you understand this, we can actually give you a question just in case you're interested. And in fact, you can try yourself. You might say that, say for example, at bus number 5, we already had P3 and another one arrived. Okay, not at bus number 5, at bus number 4. Bus number 4, another one arrived. And what was that? That is PX, and it needs 3 busts to finish its task. And then at P5, there was another process that also came there, and that is the one that we're looking at, P3. So along with P3 came PX with 3 busts, and then finally P4. If we change the arrangements, you can experiment. Like if you change the arrangements, you know exactly how to recalculate the values. And that will be quite handy, because I have seen this question quite often. This is one of the favorites, I must say. Okay, this is one of the favorites, one of the favorite algorithms for the examiners, the question setters. So pay attention to this particular algorithm. All right. Take your time to understand. If there's question, let me know. Okay. So I think that brings us to the end of this part. There's an example. There's a bit of animation, I think. Why it doesn't work? Tell me it's hanging. It's a little bit of animation in where the things are getting hanged. Wait a minute. I think I have to stop the presentation. There is a problem in the computer. Wait a minute. Yes, these are the animations that created the problem. Anyway, so once you have understand that, that brings us to the end of it. And the next part, scheduling continued, we will talk about the interactive algorithms. We'll talk about the interactive algorithms in these parts. The things that we have learned today, along with the new pack of vocabularies, the new technical words, are going to be very, very important. Well, the most important algorithm is SRT, and this is the calculation that you have. And you should try to experiment with new inserted values here and there to do the calculation. For any average turnaround time, the turnaround time for any process, there will be a waiting time plus bus time. So as I said, pay attention to these calculations because that's the way we are going to ask you the questions. All right. So we will stop here because that's what is according to our plan, that we have covered the stuff. If we move back, we've covered the topics right here. These are the topics that we covered: process behavior, when to schedule, the categories of scheduling algorithms, the criteria, and scheduling in batch systems. All right. So that is what we studied today. All right. In the next class, we will finish it off, and then, if time permits, we will ask you some questions. We will ask you some questions. Okay. And probably we will have a little bit of time because that part is not too complex and not too difficult, and we can easily spend some time asking some questions, especially focused on algorithms. Okay. That's what we plan to do. All right, I will take your quick attendance. Why did I go? As you can see your names, please respond. Xuan Huang,
Yes.
Ji Kang,
Yes.
Van Phuc, Vin Phuc, Vin Phuc,
Yes, teacher.
Juk Huang,
Yes.
Luang Ha,
Yes.
Hu Huang,
Yes.
Tan Hum,
Yes.
Nopfat,
Yes.
Din Min,
Yes.
Wakui,
Yes.
Huayan,
Yes.
Kim Tak,
Yes.
Nyat Min, Nyat Min,
Yes.
Tien Phuc,
Yes.
Wang Hui,
Yes.
Min Kuong, Min Kuong,
Yes.
Min Kuong,
Yes.
Dui Bao,
Yes.
Quay Min, Quay Min, Lim Chuk,
Yes.
Quoc Hum.
Yes.
Okay, I think all of you are present, so no question about that. Anyone sending me message? Someone send a message? Oh, okay, that was the old message. All right, so that's all, and we will wrap it up on Friday. All right. That's thank you and bye.
Goodbye, teacher.
Goodbye.